Good day everyone, I'll be your reporter for today. So at this moment, we will be tackling about hydrocarbon isomers. But before that, let's have our prayer first.
Under your grace, your mercy amazes me. Under your wings, your shadow covers me. A promise of love where my heart is safely undone. Speak to me, Lord, your servant is listening. Over the noise, I hear you whispering, my hope has come, and my heart is safely undone. I found my fortress in you, and my soul is anchored with you. My resting place is in your name, forever safe. Speak to me, Lord, your servant is listening. Over the noise, I hear you whispering, my hope has come, and my heart is safely undone. Oh, I found my fortress in you, and my soul is anchored with you. My resting place is in your name. I found my fortress in you, and my soul is anchored with you. My resting place is in your name, forever safe, forever safe, forever safe, forever safe. You are never far away, always reaching out to save my weakness, covered by your strength, and I am found forever safe. You are never far away, always reaching out to save my weakness, covered by your strength, and I am found forever safe. I found my fortress in you, and my soul is anchored with you. My resting place is in your name, forever safe. I found my fortress in you, and my soul is anchored with you. My resting place is in your name. I found my fortress in you, and my soul is anchored with you. My resting place losing your battle. Pick yourself up and dust yourself off and back in the saddle. You're on the front line, everyone's watching. You know it's serious, we're getting closer, this isn't over. The pressure's on, you feel it, but you got it all, believe it. When you fall, get up, oh, oh, and if you fall, get up, eh, eh. Tamina, mina, sangalewa, cause this is Africa. Tamina, mina, eh, eh, waka, waka, eh, eh. Tamina, mina, sangalewa, this time for Africa.
So good day once again. Before we start our proper discussion at this moment, let's proceed to our activity. For our instruction, read each statement and stand up if your answer is true and shake your head if it's false. For our first question, alkenes can have cis-trans isomers, but alkynes cannot. So the answer is true. Second, cycloalkanes and alkenes can be isomers of each other if they have the same molecular formula, and the answer is true. Third, aromatic hydrocarbons always have alternate single double bonds in a 6-membered ring, and the answer is false. Number 4, structural isomers have the same molecular formula but different connectivity of atoms, and the answer is true. And lastly, isomers have identical chemical physical properties. The answer is false. So let's start our discussion by reading our objective today. So objective number 1, to identify isomers of alkanes, alkynes, and cycloalkanes and aromatic hydrocarbons. Second, to analyze how their structural differences affect properties. And lastly, number 3, to explore their industrial and practical uses. Let me introduce you first what is hydrocarbons, isomers, or isomers. Hydrocarbons are compounds made only of hydrogen and carbon atoms. They are the simplest type of organic compounds and can be classified into different categories based on their structure. Isomers are molecules or polyatomic ions with identical molecular formula, that is, the same number of atoms of each element, but distinct arrangement of atoms in space. Isomerism refers to the existence of possibility of isomers. Therefore, the compounds of the isomers are has the same molecular formula, but different in their arrangement of their atoms. So in this report, we will be focusing on the 4 types of hydrocarbons, which include alkenes, alkynes, cycloalkanes, and aromatic hydrocarbons. So we will be examining their structures, formulas, and how their formulas are used to study their properties and behavior. So first, we have alkenes. Alkenes having double band in their structures are unsaturated hydrocarbons. Straight chain alkenes use the same prefixes as alkanes, but end in E and E. Aside from that, alkenes contain at least one carbon-carbon double band. This double band introduces the possibility of geometric isomerisms, where the position of and arrangement of substituents around the double band differs. But before that, let me introduce to you first what is cis-trans. So cis-trans or geometric isomerism. Cis isomer is a bulky substituents, atoms other than hydrogen, are on the same side of a double band, while trans isomer is a bulky substituents are on opposite side of a double band. For us to understand it well, I have here 2 structure that shows cis-2-pentane and trans-2-pentane. So we can see the cis has there on the same side, while trans is on the opposite side. So the cis and trans isomers have the same molecular formula and connectivity, but differ in their 3-dimensional structure, resulting in different physical and chemical properties. So take note for our key differences. We have here the feature, the cis isomer and trans isomer. So in group position, the isomers has two identical or similar groups are on the same side of a double bond, while trans isomers the two identical or similar groups are on opposite sides of a double bond. In molecular shape, the cis isomers has the molecule has a bent or kinked shape because the groups are close together on one side, while the trans isomers the molecule is more linear as the groups are on opposite side, reducing strain. In polarity naman, cis isomer more polar because the groups create an uneven charge distribution, while in trans isomers it is less polar since the charges tend to cancel out due to the symmetrical arrangement. And lastly, the boiling point. In cis isomer, it has a higher boiling point because it's more polar, leading to stronger intermolecular forces, while the trans isomer has a lower boiling point because it's less polar, leading to weaker intermolecular forces. So here is the general formula that we will use in alkenes. So this formula helps to determine the degree of unsaturation and predict possible isomers, which is crucial in understanding the physical and chemical properties of alkenes. So the small letter n indicates the number of a carbon, and the purpose of the 2 beside the hydrogen is we multiply the number of carbons by 2 and we will come up with the number of hydrogen. For example, so we have here the propene. So this is the structure of the propane, and if we count the number of carbon atoms, we will have 3. So if we apply the formula so the number of the carbon is 3, so C3, and we need to multiply the number of carbons by 2, so we will come up with 2 multiplied by 3 is equal to 6. So therefore C3H6. So that will be the number of carbons and hydrogen of propene. So same process on what we did sa propane. So we have here the butane. So this is the structure, and if we count the number of carbon atoms, we will have 4. So if we apply the formula, so since the carbon is 4, we will multiply 4 by 2. So 2 times 4 is 8. So therefore, the butane is C4H8.
So second, we have alkynes. Alkynes are also unsaturated hydrocarbons. They contain triple bond in their structure. Straight chain alkynes also use the Greek prefixes but a suffix of Y and E. Like alkenes and alkynes are unsaturated and have the ability to react with other substances. So here is the formula for alkynes. So as we can see, there is a -2. So the same as what we did sa alkenes, we need to multiply the number of carbons by 2 and subtract it by 2. So since it alkynes, we have a triple bond in their structure. So first example, we have ethane and the structure is this. And if we count the number of carbons, we have 2 carbons. So if we apply the formula, we have since the carbon is 2, we multiply the carbon by 2. So 2 times 2 is 4, then subtract it by 2. So therefore, we have 2 carbons and 2 hydrogen in ethane. Next is we have cycloalkanes. Cycloalkanes are saturated hydrocarbons in which the carbon atoms are connected in cyclic arrangement. They are usually represented as polygons. Each corner corresponds to a carbon atom attached with the two hydrogen atoms. They are named by adding the prefixes cyclo before the name of the open chain compound having the same number of carbon atoms as there are in the ring. They also have the same formula as alkenes have. So since they are saturated, meaning they only have single bonds between carbon atoms. So the simplest cycloalkane is cyclopropane, which is used as inhalation anesthetic. So here is the structure of cyclopropane, cyclobutane, and cyclopentane. So for us to understand it well, let's use the formula that's same as alkenes have. First, we have cyclopropane. So here is the structure of cyclopropane. So same process as what we did on alkene and same formula. So if we count the number of carbon atoms, we have 3. And applying the formula, since we have 3 carbon, 3 we multiply it by 2, so 2 times 3 is 6. Therefore the cyclopropane, we have 3 carbon and 6 hydrogen. So next we have aromatic hydrocarbons. So aromatic hydrocarbons, also known as arenes, are compounds containing a benzene ring in their structure. Most aromatic hydrocarbons are nonpolar and serve as solvent for other nonpolar substances. So since aromatic hydrocarbons containing a ring structure, it has alternating single and double bonds between carbon atoms. So these compounds are stable and have a characteristic smell. So their formula depends on the structure given. Aromatic hydrocarbons can also have a structural isomerism as well. For example, silane, which have 6 carbons and 4 hydrogen, can exist in 3 isomeric forms, such as orthosilane, metasilane, and parasilane, depending on the position of the 2 methyl groups attached to the benzene ring. So the term aromatic originates from the strong odor characteristic of many arenes. Examples include naphthalene, used as an insect repellent, and toluene, a component in petroleum products and such. So here is the structure of naphthalene and toluene. So here is the key characteristics of aromatic hydrocarbons. So first, contain benzene or fused rings. The most common example is benzene, which has 6 carbon and 6 hydrogen. A 6 carbon ring with alternating single and double bonds. The actual structure is a resonance hybrid, meaning the electrons are evenly spread out across the ring. Second is Huckel's rule. Aromatic compounds must have 4n plus 2 pi electrons, where n is an integers. Benzene with 6 pi electrons follows the rule, making it aromatic. Third, stable and less reactive. Unlike alkenes, which easily undergo addition reactions, benzene prefers substitution reactions such as replacing a hydrogen with another group. This is because breaking the benzene ring would lose its special stability. Fourth is common examples. So in benzene, we have 6 carbons and 6 hydrogen found in gasoline and industrial chemicals. Toluene has 7 carbons and 8 hydrogen. It is used in paint thinners and explosive like TNT. And lastly, naphthalene has 10 carbons and 8 hydrogen, which found in the mothballs. And lastly, applications. Used in making plastics, medicines, dyes, and fuels, found in coal tar, petroleum, and natural gas. And for our conclusion, alkenes possess double bonds and exhibit geometric isomerism. Alkynes contain triple bonds and have linear structures. Cycloalkanes are ring structures that, despite sharing the same general formula as alkenes, differ in connectivity. And aromatic hydrocarbons such as benzene have delocalized electrons that confer unique stability. And that concludes our discussion for hydrocarbons isomers, and I hope our lessons make sense to us. Thank you.